Well, greetings to you all. It's been a while since we've been together, and these are strange times. Um, this is my first attempt at trying to do a distance learning course. It's not what any of us signed up for, but we're going to make the best of this. Um, Whenever we were last together, we were talking about convergence of infinite series. And in particular, we were using the integral test to show that several series were convergent. Let me do a quick um, review of what we were doing there. Um, so we were specifically looking at the series 1 over n squared, n equals 1 to infinity, and we were show that this converges. Um, we showed this by demonstrating that the integral of the function behind the series converges. Of course, the function behind this series is 1 over x squared. And we're going to look at this from 1 to infinity. Right? And the reason this method worked at all, let's see, we'll just draw a little sketch here of 1 over x squared. And then we'll draw some rectangles which correspond to some of the terms of 1 over n squared. Right? And we're drawing the rectangles underneath the curve. And that's in order to establish convergence here. We'll see that in just a second. It's pretty clear, I think, that this first rectangle that we drew corresponds to, let's see, the height of the rectangle is the functional value at 2. And so the rectangle picture shows us 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared and so on. And so we were able to show that, well, just looking at the picture, we can see that the area of the rectangles together is actually smaller than the area under the curve from 1 to infinity. So this is certainly no bigger than the integral from 1 to infinity of 1 over x squared dx. Right? And so it's certainly true that if we put that first term over there, put it over here, that the value of the series is in fact less than or equal to this sum over here. But the integral from 1 to infinity of 1 over x squared, let's see, we're going to trick it. Can't go all the way to infinity with a integral using the fundamental theorem of calculus. So we use limits. Take the limit as b approaches infinity of 1 to b, 1 over x squared dx. And what we get here, let's see, it's going to be the limit as b goes to infinity. Antiderivative of 1 over x squared is negative 1 over x. Taking that from 1 to b, we're going to get the, again, limit as b goes to infinity. This is going to be of negative 1 over b minus a negative 1. And of course, that is 1. And so what we have is that, let's see, this integral is equal to 1. And so the series is less than or equal to 1 plus 1, and so we have that the series has value that's going to be less than or equal to 2. Now we know this is going to work because what we really have shown here is that let's see, we showed that let's see, that is clearly less than, well, we'll put the 1 on there as well. 1 over 1 squared plus 1 over 2 squared, well, that's that first term, this 1, plus this area of that first rectangle, that's less than 2. If I add the next term to get the next partial sum, that's less than 2. The next partial sum, fourth partial sum, less than 2. So every partial sum is less than 2, and these partial sums form a monotonic series, right? So first partial sum, 1 over 1 squared, that's less than 2. 1 over 1 squared plus 1 over 2 squared, that's less than 2, and so on. Right? The nth partial sum, 1 over 1 squared plus 1 over 2 squared plus all the way up to 1 over n squared, well, that's less than 2. And so what we have is a sequence of partial sums that is both monotonic, right? Every time we're adding on a positive term, so the partial sums are increasing in value. And bounded, right? They're all less than 2, so they're bounded above by 2. And therefore, the sequence of partial sums converges. And that is exactly what we mean whenever we want to say that the series itself converges. Because, let's see, right, so whenever the sequence of partial sums converges, that means that the series converges. And so that's how we were able to show that that the series where each term is 1 over n squared forms a convergent series. So in a very similar way, we're able to show the divergence of some series using the integral test. Do a little reminder as to how that worked. So one of the series that we were able to show was divergent, was the series of reciprocals of the integers. Series where each term is equal to 1 over n. The nth term is the reciprocal of the integer n. And we were able to show that this diverges. I showed it in a couple of different ways. One way, right, this is the harmonic series. One way we did that was to write out the terms and then compare it to another series. I'm gonna abbreviate this just as a reminder of what it is we did. We compared this series to the series, let's see, 1 plus a half, and then we changed a third to a fourth. Actually didn't change it. We compared it to a new series where the third term was a fourth instead of a third. And then for each of the terms beyond, let's see, how did, All right, so fourth plus a fourth, and then fifth, sixth, seventh, and an eighth. So we changed all those to an eighth, those next four terms, and then the next 8 terms we changed to a 16th. Again, not really changed, but we're comparing it to a new series. And our new series very cleverly gives us, let's see, 1 plus a half, plus a half, plus a half, plus a half, and so on. All right, so this is 1 plus half, plus a half, plus a half, plus a half, and so on, which clearly diverges, right? I add a half to itself infinitely often. I'm going to get beyond any positive number I would choose to get beyond. And so this series diverges. But the terms that I changed them to terms that were, in fact, smaller than the terms we had before, right? A fourth is smaller than a third. An eighth is smaller than a fifth, a sixth, a seventh, and so on. A 16th is smaller than a ninth, a 10th, and so on. And so the series up here is actually larger than the series here. And if this series is going to diverge, and this is bigger still, well, this series is going to have to diverge also. All right. Okay, so in keeping with the theme of the day, we were also able to show that this series converges by using the integral test on this series. And the idea is as follows, right? So we're going to compare it to the function behind the series. Function behind the series here, of course, is 1 over x. And so here we'll draw a picture of the series here along with the picture of the function. So 1, 2, 3, and so on. And this rectangle right here, let's see, that height is 1 over 1, width of 1, so the area of that is 1. The area of the next rectangle I'm drawing is 1/2. The next rectangle I'm drawing is 1/3, and so on. And so drawn in this way, what we can see is that 1 over 1 plus 1 over 2, and so on. Well, up through, let's just stop at the nth partial sum at this point. That's certainly, that's going to be less than or equal to the integral of 1 over x dx. Right, so the nth partial sum of this series, the nth partial sum is always, greater than or equal to this integral. Well, what we have, right, is that this is going to imply that the entire series is bigger than or equal to the value of this integral as we go from 1 to infinity. But the value of this integral, let's see, so integral 1 to b, 1 over x dx. We'll take the limit as b runs off to infinity. Again, we're tricking the integral here. We want to use the fundamental theorem of calculus, so we need a closed interval on which to evaluate the integral if we're going to use the fundamental theorem of calculus. And let's see, this is going to be the limit as b runs off to infinity of, well, antiderivative of 1 over x is natural log of x. And so this is the limit as b runs off to infinity of natural log of b minus the natural log of 1. Natural log of 1, of course, is 0. But natural log function goes to infinity as b runs to infinity. And so this integral diverges. And since the series has value even larger, the series is going to diverge as well. Now, both of these series, let's see, we looked at 1 over n, that diverges. We looked at 1 over n squared, that converges. Both of these series are examples of what we call p-series, and call them p-series for the following reason. A p-series, by definition, is sum of 1 over n to the, well, some exponent, as n runs from 1 to infinity. And p-series are important to us for one reason, because we can give a real quick characterization as to which ones converge, right? So the harmonic series up here, it's a p-series with p equals 1. That diverges. P-series with p equals 2 is the one we're looking at here. That converges. And it turns out that the breaking point actually is 1. As you can imagine, if I looked at the series 1 over n cubed, well, these terms, 1 over n cubed, those are smaller than 1 over n squared. And so if the 1 over n squared series converges, which it does, then we would expect that the 1 over n cubed series is going to converge also, and it does. And in fact, a p-series is going to converge for all p's that are strictly greater than 1. Right? One's the breaking point. It diverges, and it diverges for all p that are less than or equal to 1. And so that's the characterization of when a p-series converges, when a p-series diverges. And those are going to turn out to be useful to us whenever we look at other series to come.